The problem statement from Gate Physics 2022 reads as follows. The minimum number of 2 input NAND gates required to implement the Boolean expression is, we have been given a Boolean expression and we need to implement this using the NAND gates. This is a numerical answer type question, and once we find the answer, we'll fill in the blank here. So what do we mean by Boolean algebra? So Boolean algebra performs 3 primary operations. The first is conjunction. Conjunction means the output will be true only when all the inputs are true, and this is often denoted using the dot symbol or the multiply symbol. The disjunction means the output can be true if at least one of the inputs is true, and thus this is denoted by the plus symbol. Negation is whatever the input, it will be inverted. The input is high, the output will be low, and vice versa. So this is often denoted by bar, right? This is the bar symbol. All right. And the values that we use here are zeros and ones. So for instance, 0 times 0, so 0 is our value, so 0 times 0 is 0, 1 times 0 is 0, 0 times 1 is 0, 1 times 1 is 1. Similarly, 1 plus 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 again is 1, 1 plus 1 is 1. And there are 2 other laws called De Morgan's law. These are often used to convert to conjunction to a disjunction and vice versa. You can see this is converting a multiply to an addition, and with some using some negation. So solving the problems, we use these De Morgan's laws. The Boolean algebra is often implemented, the conjunction, disjunction, negation is implemented using something called the logic gates, which we see here. In the top row here, you can see the name of the gate, and these are the algebraic expression. I told you the bar is for negation. You see this dot is there, so this is multiplication or the conjunction. You see this plus, this is the disjunction, or these also called the or gate, and this is the conjunction, is also called the AND gate. You can see the symbols here. So for instance, NAND is interesting, it's nothing but the AND gate followed by an inverter. That's why you see this circle of the NOT gate here. What is a truth table? In the truth table, you list all the possible combination of inputs and you try to find the output, because we already know the algebraic expression. So for instance, let's talk about the very simple gate, NOT gate. So NOT gate has only one input. The possible combinations are 0 and 1, and this is an inverter, so it will be 0 bar, which is 1, and 1 bar, which is 0. So very simple truth table. AND gate has 2 inputs, A and B, so the possible combinations are 0 0 0 1 1 0 and 1 1, and X is nothing but A times B. So we know that 0 times 0 will be 0, 0 times 1 will be 0, 1 times 0 will be 0, and 1 times 1 will be 1. Similarly, you can do for OR gate and any other gate. The interesting thing is that the NAND gate, I told you, is AND followed by a NOT. So if you invert this 0, you'll get 1. Invert this 0, you'll get 1. Invert this 0, you'll get 1. Invert this 1, you'll get 0. That's how we get the NAND gates. Key thing to note here is that AND gate cannot be used to perform the 3 primary operations. Note, I told you conjunction, disjunction, and negation. So these are the 3 primary functions. So AND cannot do that. AND can easily perform conjunction, but it cannot perform negation. There's no way it can invert a signal, right? Similarly, OR can perform a disjunction but cannot perform a negation. However, there are 2 gates, NAND and NOR, which can perform all these 3 functions depending on how the inputs are arranged, right? And hence these are called universal gates. So why they are called universal? Because they can perform the 3 primary functions on their own using 2, 3. Let's say using 3 NAND gates, you might be able to implement an OR gate or a NAND gate or an AND gate. So similarly, just by using one flavor of logic gates, you can get all the logic gates and all the primary operations. That's why they are called universal, right? So here is a NAND gate. So this is the NAND gate you see on the top left, and we have implemented an inverter. So I'll try to solve this. So we know that the truth table of an NAND gate looks like this. So A bar is the so A and A are the inputs. Note the 2 inputs are A and A, and let's say the output Y. What is the output? We'll see. So there are only 2 inputs possible. Either both are 0 or both are 1, because both are the same, and we know that Y equal to A times A whole bar, right? So 0 times 0 bar will be nothing but 1. Similarly, 1.1 bar, which is 1 bar, which is 0. So what's happening? When the input is 0, the output is 1, and when the input is 1, the output is 0. This is nothing but a NOT gate. So when NAND gate is used in this configuration, which you see on the top right, you will get an inverter. So we saw that just by using a NAND gate, we have created an inverter. Similarly, you can create any other gate or any other combination logic for that matter just by using the NAND gates. Similarly, you can create a NOT gate from a NOR gate, and you can see here we have used 3 NOR gates to create an AND gate, 4 NOR gates to create a NAND gate. So you can use any, but all of these are the same flavors. All of them are NOR. That's what we mean by universal gate. We just saw that there are 2 universal gates. One of them is NAND, the other is NOR. Why they are called universal? Because we saw that you can implement almost you can act any combinatorial logic or any popular gate using just by NAND gates, like 2, 3, 4 NAND gates. You can do that. So here we'll implement this logic just by using the NAND gates. But first, let's simplify this. So in order to simplify this, I'm opening the brackets, not the square brackets, the inner one. It will be a b bar c plus a b bar bd plus a bar b bar times c, right? Now look at this term. What is b bar? So let's draw the truth table. So this is b, this is b bar, and let's say some output g equal to b bar. So only one input, so it can be 0 or 1. Similarly, b bar will be 1 or 0. So b bar is 0 times 1, which is 0, 1 times 0, which is again 0. So whatever the input, the output is always 0. So this term will always be 0. So this will become a b bar c plus a bar b bar times c. Now I'll multiply c inside. It will be a b bar c times c plus a bar b bar c. Now let's try to implement this logic. So c, we have 2 inputs c, and the output, let's say, is c times c, right? So the inputs can be 0 and 1. I've written that 0 times 0 is 0, 1 times 1 is 1. So c bar is nothing but c. You see what are the value of c is getting passed. So we can drop the first 1 c here, so it will become, second term remains the same. Again we take b bar c common, it will become a plus a bar. And what is the value of a plus a bar? Again, let's try to draw the truth table. So let's assume I equal to a plus a bar, right? So a can be 0 or 1. Similarly, then a bar will come 1 or 0. So 0 plus 1 will be 1, 1 plus 0 will be 1. So whatever the input, either a can be 0 and 1, but the output is also 1. I is always 1. So then this output is always 1. It will be b bar c times 1. It will be b bar c. Now we had obtained that y equal to b bar c. Let's do some change of variables. We'll assume b bar equal to p. So y will come out to be pc. And what I'll do, I'll take the negation twice. So pc bar and then whole bar. Note that taking negation twice does not change the logic. And let's assume one more change of variables. Let's say pc bar equal to q. So this will come out to be q bar, right? So y we have obtained is nothing but q bar. So we wanted the output y, and this is q bar. This is nothing but an inverter, and we know how to implement an inverter just by using the NAND gate. How do we do that? So we want here, we want to y equal to q bar. How do you do that? You say both the inputs are the same, the value q in this case, right? But q was not a variable given to us. The 4 variables that were there originally in the question, as we see here, were a, b, c and d. You can see. So final circuit should have only a, b, c and d. So what we'll do is that q can be represented in terms of p and c, right? This is nothing but a NAND gate. You see this is nothing but a NAND gate. So let's implement q. So q is nothing but the value of q is nothing but the NAND gate, right? So this is also q. And what are the 2 inputs? The 2 inputs are p and c. These are the 2 inputs, right? But p is also not an input given, right? So but p we know it's b bar. So if p equal to b bar, again we can implement an inverter just by using a NAND gate. So how do we do that? This is logic. We want p equal to b bar. So we'll simply put both the inputs to b, right? And we put this circuit here. So p equal to b bar, we know that p equal to b bar. So let's put this circuit here. So this will be something like this. Now what we see is that The only inputs that we are using are B and C, no other intermediary inputs. So P and Q are intermediaries which we have used just to simplify this. So this is the whole circuit that we have drawn now. So now we have implemented the complete circuit, and we can just now simply count the number of NAND gates that are there. It's very simple. This is the first NAND gate, this is the second NAND gate, finally this is the third NAND gate. So the question asked the minimum number of NAND gates that are 2 input NAND gates that are required. So we saw the answer is 3. But note the word minimum here. Why is it used? Because you can add, let's say you add more gates like this. This is an inverter. This will become Y bar. And let's say you add one more inverter. This will again become Y. So again, the logic will remain the same, right? The output Y will again be B bar C. But the number of NAND gates used are 5, right? But we are required to find the minimum number of NAND gates. You cannot go below 3. You cannot bypass this logic anymore. So hence, our answer for this question would be 3. Thank you for listening.